Bienvenue à ce cours d'introduction à l'astrophysique.
Welcome to this introductory course on astrophysics. In this first video, we will become more familiar with the astronomical objects in the universe, and we will introduce the distance and mass scales needed to characterize them. Let's first introduce the distance scales. First of all, in the solar system, we often use the astronomical unit, which is the distance between the Earth and the Sun, 1 AU minus UA on the slides. This distance is 149 million kilometers. That is the distance between the Earth and the Sun. If we are interested in bigger distances, we will often measure them in light years, 1y minus a1 on the slides, which is the distance traveled by light during 1 year at the speed of 300,000 kilometers per second. This corresponds to a distance of 9.46 times 10 to the 12th kilometer. Most of the time, we will use another distance, called the parsec, that we will define in the following. It turns out that this distance, numerically speaking, is equal to 3.26 light years. To define a parsec, we first have to define what is called the parallax. Parallax is the angle subtended by Earth's radius at a distance d. For example, at the distance of this star. Here is the line of sight to the star seen from Earth at a certain time. The star will be at a particular apparent location on the sky. 6 months later, for example, the parallax of the star will be different. The star will be observed at another location on the sky. The angle variation between the two positions is called the parallax. So, the parallax is an angle theta, which depends on Earth's orbital radius and on the distance to the star. During the year, what we will see on the sky is the star following small eclipses, whose opening angle is equal to this parallax. The parallax is simply theta equals r divided by d. We can now express things in astronomical units. If r is equal to 1 astronomical unit, and if theta equals 1 arcsecond, then we can write a very simple equation. 1 equals 1 divided by d. This obviously implies that d is also equal to 1. This 1 has the unit of a parsec, which is the abbreviation of the parallax of 1 arcsecond. In other words, if we express distances in astronomical units and parallaxes in arcseconds, then we can rewrite that the angle theta in arcseconds is equal to 1 over the distance in parsec. That is, a parsec is the distance at which 1 astronomical unit subtends an angle of 1 arcsecond. Those are the main units of distances in astrophysics. Astronomical units are used for distances of the order of the size of a planetary system, like our solar system. Otherwise, we use light years or parsecs. We have a direct relation between distances in parsec and angles subtended by objects in the sky. Now let's define some units of mass. For example, in the solar system, you have here the planet Saturn, observed at different times. In our solar system, we have 8 planets. We can express their masses either in Earth masses, for telluric planets, that is with a solid crust, or in Jupiter masses, for gaseous planets. The symbol used for Earth is a circle with a cross in its center. The Earth's mass is equal to 5.97 times 10 to the 24th kilogram. Earth's radius is 6,371 kilometers. We will often express planetary masses and planetary radii in units of Earth masses and Earth radii. If we are interested in bigger planets, we can compare, for example, Jupiter mass, which is 317.8 times the Earth mass. and the radius of which equals 11 times Earth's radius. In addition to the 8 planets of the solar system, we currently know 1,700 exoplanets, or extrasolar planets. The first extrasolar planet was discovered in 1995 by Michael Mayer and Didier Queloz at the Observatory of Geneva. This one was an indirect detection, measured thanks to the radial velocity of the star around which it orbits. The first direct detection was made in 2008. In the solar system, we don't only find planets. There are also comets, for example, which are sort of frozen mud balls that evaporate as they get close to the sun. The matter ejected by the comet, by its nucleus, is pushed by solar photons along large cometary tails. So, comets have a nucleus. The nucleus is often very small, with a diameter of the order of 5 to 10 kilometers, with a maximum around 100 kilometers. They also have a halo. Its diameter is of the order of 50,000 kilometers to 250 kilometers. Cometary dust is ejected to form tails. For example, we see here a dust tail made of quite heavy particles. And here a tail made of ionized matter, namely ions. Light particles are over there, and heavier dusts are generally ejected on another tail. What is the composition of a comet? They are mainly composed of organic matter, C, H, O, N, and actually contain 80% of water, and around 10% of carbon monoxide. Such cometary tails can reach the size of the order of 60 to 100 million kilometers. We have then sizes of the order of the astronomical unit. Let's resume our tour of the solar system. The solar system contains, of course, the Sun, our reference star. Note that it is the only star we know that we can directly observe the surface, that we can take pictures of. All other stars are way too small and too far for us to directly study their surface. The surface temperature of the Sun is 5,700 Kelvin. This is the mass of the Sun that will be used as a reference for the mass of other astronomical bodies. We will generally express the masses of galaxies and large astrophysical objects in terms of solar masses. This solar mass is 10 grams. Here is a solar radius that will also be used to characterize the radii of other stars, for example. Its value is 695,000 kilometers, which is roughly 109 times Earth's radius. Other stars are similar to the Sun. They are powered by two phenomena: gravitational compression and nuclear fission of hydrogen atoms into helium. We usually define the lifetime of a star as the time it takes to burn all of its hydrogen into helium. This amount of time is the main part of a star's lifespan. The other extremely important parameter for stars is their masses. Star masses can range from 0.06 times the mass of the Sun up to 60 solar masses. Under 0.06 solar masses, nuclear fusion reactions cannot ignite. Beyond very large masses, such as 60 to 100 solar masses, the star will collapse and thus disappear. Stars' radii, that we will compare to Sun's radius, will range typically from 0.17, 0.2 solar radii up to approximately 15 times solar radii. This is the whole range of radii we can observe on stars. As for temperatures, the Sun has a surface temperature of 5,780 Kelvin. The coldest stars can have temperatures of the order of 2,640 Kelvin, and the hottest ones around 44,500 Kelvin. The lifetime is, as mentioned before, the time needed to burn hydrogen into helium. This time varies on a very wide range that can go from 5 times 10 to the 6th, a few million years, up to 10 to the 13th years. A star can last longer than the current age of the universe, 13.7 billion years. Star's luminosity will again be compared to the Sun's. Typically, the luminosity can vary between 1.2 times 10⁻³ solar luminosity. 1,000 times less luminous than the Sun, and up to stars as bright as 8 times 10 to the 5th solar luminosity. Most stars are in mass, radius, temperature, lifetime, and luminosity ranges that are written here. Stars do not have an infinite lifespan. Once they burn all their hydrogen into helium, there are 2 possible scenarios for the death of a star. Either the initial mass of the star is bigger than 8 times the Sun's mass, and we have a supernova, a very powerful explosion of the star. Or the mass is lower than 8 times the mass of the Sun, and we have what is called a planetary nebula. Unlike what the name suggests, a planetary nebula has nothing to do with planets. Here is one of them, Nebula Messier 57, in the constellation of Lyra. Planetary nebula are due to the expansion of the outer layers of the star and the collapse of internal layers. At the end of the process subsists at the center what is called a white dwarf, surrounded by the star's remnants. It is the white dwarf that will ionize the gas all around the nebula. In the external layers here, we recognize radiating hydrogen with red spectral lines. And in this part in green is the radiation of oxygen. Here is the expansion velocity of the nebula, which grows as the gas expands all around it. The expansion speed is of the order of 20 to 30 kilometers per second. In a supernova, the speed of the external layers, much later after the explosion, is of the order of 2,000 to 3,000 kilometers per second. The matter ejected by stars at their death, either by a supernova or in the form of a planetary nebula, will be recycled into new stars. Here is the example of a great Orion nebula, Messier 42, which has in its center a cluster of young stars forming from the gas in the nebula. There are a lot of things in such picture. There is ionized gas, the density of which is around 1 particle per centimeter. That is a mass density of 10⁻21 kilograms per meter. Here the gas looks quite dense, but we actually see the nebula from far away, and the density is in reality lower than in the ultra-high vacuum we can produce on Earth. This concerns the gas that will emit a spectral line radiation at different wavelengths, which is generally produced by a hot source, such as a cluster of young stars, namely stars forming from the matter ejected by the death of other stars. We will also find cosmic dust. Dust absorbs background light, which is why we see all the dark stripes. Here or there, these are areas filled with dust. This dust is composed of grains bigger than the gas, itself composed of atoms. Dust grains are actually similar to the dust left by chalk on a blackboard, for example. This dust has a density even smaller than the gas, for example, 10⁻13 particles per centimeter. which is 13 orders of magnitude smaller than the gas density. The mass density is 10 minus 23 kilometers per meter. We can, of course, imagine a situation where all the gas has been recycled into stars. It is usually the case in what we call open clusters. For example, we see here in NGC 4755 a variety of young stars, here and there. All the blue stars in this cluster are at the same distance from us. The stars in the cluster have approximately the same age. The stars in this open cluster are very young, with an age around 10 to the 8th years, which is small in comparison to the age of the universe, around 13.7 billion years. The size of such a cluster is around 10 parsec. It is also the size of the nebula who gave birth to such clusters. In a galaxy like our Milky Way, we find young stellar clusters, open clusters, and non-open clusters, as well as globular clusters, such as this one here. A globular cluster is much more massive than an open cluster. The typical mass of an open cluster ranges from a few hundreds to a few thousand solar masses. The mass of a globular cluster is of the order of 10 to the 6 solar masses. Globular clusters are relatively old star clusters. The age of the stars is of the order of 10 to the 9th up to 10 to the 10th years. Such clusters can be found in the periphery of galaxies. They are bigger than open clusters, with typical diameters of 40 to 50 parsecs. Stars, planets, nebulae, star clusters are all elements of galaxies. A galaxy is a much bigger object than everything we've seen so far. Here you have a spiral galaxy, like our Milky Way, which is named after its spiral structure that you can see in a disk with a bulge in its center. So here's the bulge, and here is the disk. Old stars are in the center, while young stars are usually formed in the arms. What we don't see in this picture is a halo of the dark matter all around, in which are also the globular clusters. At the scale of this picture, the previously seen globular cluster is completely invisible. If it was visible, it would appear as a tiny dot, just like these. As for the diameter of a galaxy, you remember stellar clusters have sizes of 10, 40, 50 parsecs. Here we have galactic disks with a diameter of 30 to 40 kiloparsecs. The mass of a spiral galaxy is of the order of 10 to the 9th up to 10 to the 12th solar masses. Here is another example of a spiral galaxy. As mentioned before, in a spiral galaxy, you have a bulge here and a disk that you see now here, edge on. This is the spiral galaxy NGC 891, seen edge on. What you see here is a halo around the bulge, composed of old stars. Here are the spiral arms seen from the side, composed of young stars, and of the dust absorbing the background light, just like we saw earlier on with the nebula Messier 42, the Great Orion Nebula, that was showed as an example of diffuse nebula. In the disk, you have dust and young stars. The Milky Way looks like that. Obviously, we can't see our own galaxy from outside, but if we could see the Milky Way from outside, we would place the Sun here, at 2/3 of the distance between the center of the exterior of the galaxy. Again, the whole system is surrounded by a halo of dark matter that, by definition, does not emit any light. Spiral galaxies are one kind of galaxy. There are also elliptical galaxies, which, as their name suggests, have an elliptical shape. They are often at the center of galaxy clusters. This is why you see here other galaxies around it. All these galaxies are at the same distance from us, and the central galaxy is an elliptical one, which is actually a sort of ball of old stars with random orbits around the center of gravity. Contrarily to spiral galaxies, they contain little or no dust. They also contain little or no gas and form only a few stars. Their masses covers a much wider range than spiral galaxies, between 10 to the 7th and 10 to the 13th solar masses. They are generally encountered at the center of clusters of galaxies. This is a cluster of galaxies. At the center of a galaxy cluster, we usually find a main elliptical galaxy, as we can see here. We actually see a lot of elliptical galaxies, even quite far from the center. There are also spiral galaxies and virtually all types of galaxies. They all orbit around a common center of gravity. Galaxy clusters are the heaviest gravitational bound structures in the universe. They obviously contain visible matter, but are also surrounded by a halo of dark matter, just like individual galaxies. Spiral galaxies, elliptical galaxies. The masses involved are really huge, between 10 to the 14th to 10 to the 15th solar masses. All the astronomical objects that we just saw, from the smallest to the largest, the lightest to the heaviest, are part of a whole, the universe, the study of which is called cosmology. In the picture behind me is an overview of the whole universe. In a single picture, this is the Hubble Ultra Deep Field, a picture taken by the Hubble Space Telescope that simultaneously shows in a single shot 10,000 galaxies, illustrating the diversity of the world surrounding us. It is by studying such pictures in details, at different wavelengths, different resolutions, and perhaps at different eras, that we can trace down the history of the galaxy's formation, stars, planets, in short, the whole universe. Two essential tools to study the trajectories of astrophysical objects and measure their masses are the three Kepler's laws and the virial theorem. These will be the topic of the next videos.